Today I'll discuss a video denoising technique using low-rank matrix completion. Uh, Even though there's a lot of advances in the sensor design because of the webcam, mobile phone cameras and low-cost cameras, there's always a noise introduced in the videos. The video denoising technique, it mainly aims at removing all the noise in all the frames of the video, like collecting information in both the spatial and temporal domain. Most of the existing video denoising techniques, they rely on a only single noise. Like they consider the Gaussian noise to be the more affecting part, and they put the techniques for removing the Gaussian noise from the video. The current algorithm which I am going to discuss, it aims at removing the multiple sources of noise, like the real-time noise. If we see in any of the video denoising technique, if we do not consider the exact real noise which is present as the statistical noise, then it cannot be a good technique. So these people, they try to remove the heavy Gaussian noise, impulsive noise and Poisson noise. Some of the other related techniques include BM3D, VBM3D and PCA based methods. BM3D and VBM3D are similar as the present technique, but the denoising and the procedure followed is different, as the current algorithm and BM3D, all of them, they take the patch matching, and then they put the filtering techniques. Like in BM3D, they first do the patch matching and then do the filtering, Wiener filtering. I'll explain the block patch matching algorithm in the next slide. But another advantage with the current technique which I am going to discuss is, first they do a pre-processing of the video using an adaptive median filtering technique. After the pre-processing step, they do the block matching, and after the block matching, they perform the matrix completion on those blocks to get a noiseless video. The problem which we have is, suppose consider a video F with K frames. Then it could be, if it is a noisy video, then each frame Fk could be a sum of a clean image and a noisy image. So what the aim of our technique should be to get the clean image, avoiding the noisy image. So how to get only a GK by removing the NK is, first we consider all the videos and then perform the pre-processing denoising step, as I said, the adaptive median filter, which I'll discuss about the adaptive median filter in the next slide. After performing the adaptive median filter, now all the frames in the video is like free from the impulsive noise. Not from all the noise, but that should be sufficient for us to perform the patch matching. In the patch matching, if we have first consider the first frame of the video, in that we consider a 8 by 8 pixel one to be the patch, that's a PJK. In that we put it as a reference patch, and in all the current next frames, we try to find out the similar patches as that of the reference patch. After finding those similar patches, we'll put all those in a matrix, like I'll explain in detail. After putting in a matrix, then we remove all the unreliable pixel values, and we put only the reliable pixel values in the matrix, and from the reliable pixels which are noiseless, we do the matrix completion on that, and we get a matrix which is a noiseless one.
How we can find the reliable?
Yeah, I'll explain. First, I'll start with the.
How to define the similar frame of?
Yeah, I'll explain the technique. Yeah. First, I'll explain.
And another question. You said in the first image you select some window, and if this window has some noise.
Yeah. Like first we consider the video. We'll remove the noise, only the impulsive noise from all the video, all the frames, and then we select a patch of 8 by 8 pixel size. And seeing that pixel, we'll see how many of the next frames have the same image. In that way, we'll select the reference patch, similar patches.
Only from the first frame?
No, from the next frame.
Selecting the first
Like
frame?
select a reference patch from the K frame, and then from the K plus 1 frame, so on till K plus M frames. Now first I'll explain the pre-processing denoising technique, that is the adaptive median filter technique. some of the advantages we have with the adaptive median filter technique over the median filter is, now if we consider the median filter technique, it will be like the median filter will be on each pixel on the every pixel one by one. But the adaptive median filter, it will see if there is a impulsive noise is present in the one. If it is present, then it will perform the filtering, or else it will not perform. In this way, more details will be preserved. It's not like even though there is no impulsive noise, still the median filter will perform its filtering technique sometimes. So adaptive median filter will not perform. So first it will perform a testing, like the level 1 and level 2 testing procedure. If the testing fails, like in the test, if it is proved that there is an impulsive noise, then it will perform the adaptive median filter technique. How the technique is performed is, it's a two level procedure in the level 1 and level 2. Generally, impulsive noise, we say it will be a positive impulsive noise and a negative impulsive noise. Generally, how a median filtering technique is performed in a one-dimensional space is, suppose consider a data set of 2, 6 and 3 to 4 values. On this, if we perform the median filter technique, if you see, this value could be a noise because this is maximum, it's very bit higher when compared to the other values over here.
So it's considered as a time series.
Sorry?
It's a time series.
Yeah, this is a one-dimensional space. In one-dimensional space, this is how the median filtering technique performs. If this is a data set which contains 2, 86 and 3 as values, like the first window, because this is the first element, it doesn't have a previous element, we consider the same one twice. And the last time, because this is the last element, we don't know the next element, we consider the same element, same value to be there. And first consider the first 3 and put it in an ascending order, and then put the median of that
How you can
output.
find 2 to 80?
This is the first element. We don't know what the previous element will be.
Okay.
So we consider the same element to be the previous element also, so we put twice. And then calculate the median of that element. In that way, the median filter output would be a 2663, which says that all the pixels will be in the same range.
X is as a block.
X is the input. Yeah, it's like in a matrix if we consider the pixel values.
Yeah.
It's like that. So this is how the median filtering technique works. So we will see the calculate the impulse, like if it is higher, maximum or minimum, and then do the median filtering technique over there. Similarly,
So can you second line is 280
280 and 6.
bias you say.
Sorry.
Oh,
Okay.
Okay.
And then put in the ascending order and then put the median.
So you fix the window size of 3 and you move the
Yeah,
window.
move the window. Like window size, if we always consider it in the odd terms, like it could be even also. If it's a odd, it will be easy for us to calculate
yeah.
the median.
Yeah.
So,
So what if there's a flash in the movie? Like yeah. Then it's dark.
it's
Flash.
dark.
And
Yeah,
then
it will be the
it comes
minimum value. So So we'll try to put the median of the.
Yeah, so it's become dark again.
Yeah.
If noising is more than 3 pixels,
I guess it's time series.
it's not. It's the image.
No, is it
Image.
block?
Is image or time?
No, it's block. It's an image.
In the block, in the image, it's just an example of 1D, but in the image it will be 2D. So we'll take it
Oh,
3 by
okay.
3 matrix and then.
Block of 2
block, yeah. So in similar case, in a 2D case, if we see, this is the adaptive median filter technique. So instead of performing the median filter on, like here we are performing on each window, on every term. Instead of that, first we will see if there is an impulsive noise present in the block. If it is present, then we'll perform the median filter. If the noise is not present, then we'll not perform the median filter. So again, if the noise is present, we can preserve those details.
What is impulsive noise?
Impulsive noise, it will be, suppose the pixel values will be normal, the impulsive noise would be a maximum or a minimum noise. It could be 0 or 255 values in the middle.
So it's
More the pixel.
pepper and salt.
Pepper and salt and pepper noise.
Greater be
Yeah.
minimum or
Minimum or the maximum, black or white.
So maybe that 80 could be.
Yeah, it should be a noise, so it's replaced by the surround light. The
Uh-huh.
value close by. Because of the image, it will be like 63 the pixel values. But in the middle, if the salt and pepper noise, like a black particle is a.
This means that you can just see all
Yeah,
of them.
just see. So see the median range, how the range is, and according to the range, will change the value. That's what median filter is. In the adaptive median filter, instead of performing on each one, we'll see if noise is present or not, and then we'll perform the median filtering on that window.
Oh yeah.
Like only for this window it's needed to perform the median filtering. For the above ones, if there is no noise, it's not needed to perform the median filtering technique there. For these ones, it's the same. Only this one is changing. So in the adaptive median filtering technique, we'll perform the median filtering on just this window, leaving the rest of the windows.
Because 80 is the middle.
Yeah, if noise is present only in this window, so we'll perform the median filtering technique on this window, leaving the rest of the windows. That's what is adaptive median filtering technique is. We'll see like select a window size, like if it's like I said, it's a 8 by 8 pixel patch. And then we'll select a window size to be 3 by 3 or 5 by 5, like both of odd, so that the median could be calculated easily, odd number of values. So in that window size, we'll calculate the x median, that is the median of that window size, and then what is the maximum intensity in that, and what's the minimum intensity. And then we'll subtract the minimum and maximum intensities from the median. If both of them are, if T1 and T2 are two hypotheses, we consider one to be the positive impulse noise and the other to be the negative impulse noise. If both of them are present, like if this is greater than 0 and if it's less than 0, then we consider that it doesn't have any impulse noise and we go to the next testing procedure. If suppose there is, if that condition is not satisfied,
So what's A1 and A2?
it's like they gave it two tables.
What's A1 like in the pieces?
Like the T1 and T2.
You write A1 and A2.
Yeah, I just copied this. A1 and A2 are T1 and
Everything.
T2.
Yeah.
Suppose consider a 3 by 3 to be. This is the median of the window.
X.
5. It's 5.
This matrix is X.
This is the window size which we consider. X is the 8 by 8 pixel, of which this is the window size which we consider. Yeah. X median will be 5 and the minimum will be 1 and maximum will be 9. So we calculate the A1 and A2, that's the T1 and T2 which I said. One should be X median minus X minimum, so it will be 4, A will be, and A2 will be minus 4. So it satisfied the condition like A1 is greater than 0 and A2 is less than 0. If this condition is satisfied, then according to the truth table, it is said that it doesn't have any
How
noise.
can I find A2 as a -4?
A2 is equal to T2.
Yeah, T2.
It's minus A1.
It's
The T2 is equal to minus T1.
no. T2 is equal to x median minus x max. Maximum intensity in the window
yeah.
size and the median value.
But
Limit.
it always satisfies, right? How can it be not satisfied?
If there is a impulse noise in the middle, suppose if there is a minimum noise, like a negative noise, in that case the case will not be satisfied.
But the medium will always bigger than the minimum, right? And the medium will always smaller than the maximum, right? No matter what you have.
I don't think it's needed. Suppose the median value is 80 in the middle, then it will not satisfy.
Oh, okay. That one
Medium.
is not the medium, right? The medium here is equal
Medium.
to.
Oh, it's the center of the.
Yeah, it's the center of the window
Not
size.
the median value of the array.
No,
Yeah.
median is what is the center element in
Okay,
the
that is not medium. You said like T1 and T2. That's not its medium. It's
MED is the median value of that
But you said
window.
like it's. But you just said like that is 80. The median here is not 80, right?
Median is this value, I said. X median.
Now if you draw the 80 as a middle.
80, then the median will be 80.
No, the medium is not 80. That's not the definition of medium. Medium is equal to.
No, it's not median. It's the
Big.
center of the.
Center of the center.
Yeah, the
pixel.
definition
So
is.
I guess
that's
the-
two different terms here. You need
The
to
definition
I
is.
guess
you need to make sure what you're talking about
I guess
here.
in statistics they call median the middle of the array.
Yeah,
If you
median is the middle of
sort
the.
that, you sort that array and then the middle is the median.
Yes. This is
So
the middle of
this
the-
one is you need to sort that and put and get the middle one is called median in statistics. But this one is kind of geometrical center of the region.
Okay.
So
Hmm.
yes.
1, 2, 3, 4, 5, 6, 7, 8. It's 5. But if
Yeah.
you use 80 is here, and it's 6. Oops, no.
Yeah, in this the middle element will be the median.
Yeah, but
Yeah.
now it's 80 is the X min,
Yeah, X median.
but which definition? This definition? Oh no, just center of the that
Just
block.
center of that block.
No. You can't call the center of the block as medium. No one called that. No one ever called that.
Okay. It's they're checking if the centered pixel is errored or not. If it's error, then they'll
But I
change
guess it
the.
doesn't make sense still. Like, why do you want to track the center only? That defeat the purpose. You want to compute the median and stuff like that, right? I'm more looking into like that it's not A1 bigger than 0, but A1 is like bigger than some threshold, stuff like that. For example, that would determine whether you have a spike there, right? For example, if you have a spike there, like what you write there, if you have a spike there, then your maximum becomes 80, right? And your medium will become like
Yes, then they
Six.
even the median will be the centered pixel.
Then no,
Like only
that's
if you
not
consider
medium.
okay, no,
Let's
median.
take
Just
yeah.
centered pixel.
No, that's what I'm saying also. Probably it doesn't make sense to look at the center of the pixel. Why do you even want to look at that?
I guess she's moving the window, so if there's noise, the window will eventually center at the noise point.
So
The-
Then why do you want to compute medium like previously? And the problem is that the title is called adaptive medium filter. So I'm thinking like the medium will appear somewhere, if the title is really adaptive medium filter.
I think the middle pixel will be changed with the median value. For example, we test the middle pixel of the window, and after that, if it's impulse, we
But actually,
exchange it with
Do you
some
have the
middle
paper
value.
here?
Yeah,
Like,
I
can you
do.
put it up like on the go down?
I can just find the center. Okay.
Go down. Like that. So which one is your A1, A2 here defined?
Here it's the T1 and
So where's its median defined there? Yeah, I don't think that is the center of pixels. That's the median. But let's go down to the T1, T2 again. So how is it going to use the T1, T2? Like, can you,
the truth table. H3, what they say is the SIJ, which means no noise present, non-impulsive one. So if the output of that would be a H3, that means there is no noise present, and we can go ahead without performing the filtering. If the above three cases like A, B, C will be the case, then it indicates that there is noise and they perform the median filtering on that window.
We go up to the definition of the mixed mean.
go back to the table again. So what the hypothesis there, like H1, H2, H3, where's the definition for those hypotheses?
H1 says that the X median will be a minimum value. The H2 is the maximum value for us, and this is the Sij. Sij indicates it doesn't have any noise, and it's uncorrupted value, uncorrupted pixel. So if the hypothesis, if it's a positive and negative, then it comes to H3, which means no
Does
noise.
it do any preprocessing when they include the X? Like the X is just pixels or like
S,
X here?
X mean,
So it's just some input?
yeah.
Okay.
Set
Go to
Sij
Sij.
equals 0.
Don't move too quick. So that one is the first level, and then second level.
In the first level, if it is proved there is no impulsive noise, then in the second level they will see if it's
Is
present.
that X time is 0 or arrow?
Oh, okay. There's no pattern line. So SRG can only be 0. I guess, So you may continue, but that's the medium, it's not the center of the block. The medium filter, yeah. I know, I mean, but what do you want to say? What do you say? Okay, medium filter is very old stuff itself, so I'm curious like the adaptive whatever the paper is responding. So the whole idea is just like if you have a mean filter, like for example you take average, then if you have outliers, that's basically spike will take into account. I mean you basically will affect by those spike, those outliers. But instead of use medium filter, basically those outliers will disappear. So that's it. But I never read that paper, so I don't know the adaptive one, which part they want to do. Anyway, just continue, yes.
The adaptive median filter is the pre-processing step to remove the only the impulsive noise present in the video. After removing the impulsive noise, the video will be a bit okay to perform the patch matching and grouping part. In the patch matching part, in the current frame, we'll consider a 8x8 pixel patch, and we'll like measure the MA, that's the mean absolute difference between that patch and the same 8x8 pixel patch present in the next frame. And after calculating the mean absolute difference between those two frames, we'll calculate a motion vector. Fast algorithm, almost there are many exhaustive search patch matching algorithms. In those algorithms, it will consider the each and every pixel in the whole 8x8 patch. But the fast algorithm, in the sense, it says that it will be a subsampling of 4:1 ratio. Like as it said, the A, B, C, D, it's a regular pattern they consider. And for the first time, they'll just consider the A. Wherever A is present, they'll calculate the MAD only for the A pixel. Like they'll start from the first 8x8 matrix A. From here, if they start, we consider this current location to be x comma y, it will go ahead as x plus y and y plus j. So first this A will be matched with the this will be a patch in the first current frame, and the other similar one will be considered in the next frame. And this A, the first upper left pixel will be compared to the first upper left pixel in the next frame, and then this will be incremental one, and then it will come to the next A, and then like this only the A terms in this patch are compared to the next frame. In this way, like in the exhaustive search, it will perform the search between, like the similarity, to find the similarity between those two patches. It will perform the MAD, that's it will calculate the mean absolute difference for each pixel. But what they say is, like if it's a video from from the current frame to the next frame, there will not be a lot of difference in the image. It will be just a small difference. But that there's no need to calculate the absolute difference between the each and every pixel in the two frames. So it will just consider as like, so if we see this, it will be just a 1/4 part of the pixels are being considered for checking if they are similar or not, leaving the rest of the terms. In this way, the computational complexity will be reduced, and the search block could also be performed. And it's suppose if we consider like this patch is a n by n patch, then the computational complexity of this patch could be, where L will be the number of locations we search and K will be the number of operations that will be performed per pixel, like the absolute difference being calculated and all that. If we do the subsampling procedure, like it's a 1/4 ratio, then the complexity will be reduced to, it will be 1/4. So in this way, they'll just consider the first all the A's and see if they are similar, and then the mean absolute difference will be calculated for all each.
Squared by 4 or it's squared by 6?
N squared by 4, because it's the by 4th sampling ratio. Because A, B, C, D, 4 terms are present,
Yeah.
and we're just considering for the A. So it's 3/4 of the.
Why you just pick up just 3 of the A.
No, just not like everything will be sensitive. Each of the
Out of the A.
because if we increase the I and J, right, it will almost all the A's will be covered in that patch. With 0, 1, this will come, and 1, 0, this will be active. Everyone will come. Exhaustive search algorithm, this one is more faster than the exhaustive search patch matching algorithms, which the other video denoising techniques used. So the computational complexity of this video denoising technique will be less compared to the other ones. The motion vector, how it will be calculated is, minimum absolute difference between these two pixels will be put into this vector, and that becomes a motion vector, which we will use for the to see if it's a similar patch or not. In this way, by using this technique, we can calculate the similar patches which are present in the video. After selecting those patches, we'll put it into a matrix of PJK. Suppose after performing this patch matching algorithm, we'll come
What's
to know.
MAD?
Sorry?
What's MAD?
It's the mean absolute difference.
Okay.
Should I explain?
No, it's fine.
After doing this algorithm, the patch matching algorithm, suppose we come to know that for a patch X, m patches are found similar, then it will be written as all the m patches will be put into this m. Like each patch which we get, we will concatenate all the columns into a vector and put it into a matrix forms. Finally, we'll get a PJK matrix, which will consist all the P1JK, 2JK, so on to MJK. So it will be a. Suppose we consider a 8 by 8 patch. The number of will be 64, and this will be m.
Can you explain this again?
Yeah. N patches are found similar for the reference patch which we considered in the first frame. Okay. Now this P, it contains all those n patches. Like suppose if it's an 8 by 8 patch, we'll concatenate into a single column, like all the columns and rows of that. So this will be a 64 rows present in it.
So the m patch is similar, is from the frames after the reference frame.
Yeah, after the reference frame. Like if I take a
Top
video
M.
of you, the next.
Top m similar patches. You can find like more than m, but you only get the top m.
Yeah. No, like all the M, will find M similar patches in the whole video.
Okay.
M similar patches. So we'll concatenate all those elements into a single column and all the M similar patches. So it will be a M by N square by M matrix. Is it clear?
What's the idea?
J and K is this one, the patch matrix. Sorry, it's the N square by M matrix.
What was the I?
I is M. We found M similar patches, right? So that will be the M. I will be M.
Excuse me, what's the similarity measurement? Similarity measurement for finding its how to
Finding how many patches
Yeah.
M. We use a mean absolute difference. Like the mean square error between the current frame and the next frame, we'll do the mean absolute difference and then calculate how many similar patches we have. Show in the video. MAD is calculated like this. Fn is the current frame and Fn minus 1 is the previous frame if we do. Then the intensity at that particular, the top position which we consider, the upper left pixel. K plus R.
I think this is a number, and what's your mapping between this number to singularity?
Yeah, to check the
How do
similarity
you,
and then
how you,
and then we get this vector. In that vector we'll put the minimum MAD values which we get between those two patches. Is this clear how we get the PJK matrix? Again, as we said in the first slide, now the PJK will be a sum of the clean image and the noise image, because we just performed the pre-processing step to remove the impulsive noise, and because all other noise will be present and we need to remove this, and the goal of this will be to calculate QJK finally. To find the QJK, before that, now the PJK, it contains the noise and all the so in order to remove that and make it a missing elements matrix which contains only the reliable elements, we'll perform two procedures to remove those elements. In the first part, again the same technique, like I said and explained clearly, the adaptive median filter technique is performed to check how many of the pixels are corrupted with the impulsive noise. And if it finds any of the pixels that are corrupted with the impulsive noise, it will remove all those pixels and make those pixels values to 0.
So you assume you don't have this value, and then you try to fill
Yeah.
in these
Now
holes
the
with your...
PJK matrix is a complete matrix. In that we'll see which of the terms are corrupted by impulsive noise, and we'll put those values to 0. All the pixels which are corrupted by impulsive noise. And then make all those values into a subset and put it in that. And the other, after removing the impulsive noise affected pixels, then we'll calculate the mean of each of the row vector. Of each row vector, the mean is calculated. And we'll see how many of the terms in each row are more deviated than the mean. Like if suppose the mean is 5 and then one of the term is 100 or like that, then all those terms will be made 0. Only the terms which are close by to the mean are kept in that matrix, removing all the rest of the term, like rest of the pixel values. So now the matrix PJK contains only some of the elements of the complete matrix, in which the values are a bit close to the mean value. So now PJK will be a missing element matrix, and all those elements which are present in this PJK right now are the reliable elements which does not contain any noise because it's close to the mean and it's similar to.
So you remove value twice. The first time
Yeah,
you remove
twice. The first time we remove those pixels which are corrupted with the impulsive noise using the adaptive median filter technique. And then removing innocent, put those values to 0. And after that we perform this row vector mean filtering technique. In that we'll calculate the mean of each of the row vector, and then whatever the pixels in that row are far away from the mean, those will be assumed 0.
That matrix is your PIJK matrix.
PJK matrix here. Before it was in the vector form, we kept PIJK and then we concatenated those into a this is the reference patch and then we found M similar patches. All those patches are arranged in each column by concatenating the whole batch. And so now because we considered a 8 by 8 patch, so the number of rows, because after concatenation it will be 64 and then M. So then of the PJK matrix will be a P64 by M matrix. But in this matrix, we remove the impulsive noise and those pixels whose values are more than the mean. So finally, we'll be left only with the reliable pixels. On the reliable pixels, we perform the matrix completion algorithm, so that during completion, we'll get the noiseless image.
So, which one is your so what entries in the matrix are lot long? Like you said use matrix completion, right? So then some of the elements in the matrix is basically unknown, right?
Yes.
So where the unknown there and which one?
Now whatever are the pixels, the elements which have impulsive noise, we make them to 0, and the other next terms also, the next ones which are far away from the mean, we make it 0. Now we consider those to be the unknown values.
Okay.
What will happen if the true value is equal to 0? So how can you differentiate is the true value 0 or is the unknown value 0?
For each row vector, we calculate the mean. We assume that from the whatever are the values which are far away from the mean, it does contain some type of noise. That's why it's more brighter or more like that. So and we remove those terms, those pixels.
Why do you want to set it to 0 instead of just say it is unknown?
Yeah, to make it unknown.
But
To make it a low rank, so that we can put the
Why
matrix
not?
completion in there.
yeah, but why not just a star there or some symbol just to indicate the element is unknown? Why do you want to make it
Like finally, after we'll just whatever are the values left over, we'll put that into an index like the gamma index, and then from that we'll perform the matrix recovery problems. These values are not considered, like whatever we make 0, we'll just put the only things which we need are the reliable pixels. That we'll put into an index, and then from the index we'll do the matrix completion.
So they are not 0 and not set to 0. Because when you set
The
it-
impulse noise values are set to 0.
But
So do
why
you-
you want to set to 0?
Do you use the 0 value after?
No, we'll not.
Okay, so it's similar to set to invalid.
Yeah.
But the pixel value start from 0, right? The pixel is start from
Mhm.
0 to
Yeah.
255. So how can you differentiate if a pixel value or is a unknown?
For example, if you
Yeah,
have
I-
a mean equal to 0 in some rows, what
Mhm.
happened to the another pixel values? For example, in the special row, you have a mean, it's near to 0, and based on this, you must change all of the values to 0, and you cannot detect which one is the real value and which one is the unknown value.
Like what they say, the set of missing elements of PJK have two subsets. The first subset, it contains the impulse noise value, and the second subset, it contains those values which are away from the mean.
We put this into a set.
Into a set.
You
And the
mark
rest of
it.
the elements are kept into an index set, into a set. And we'll
So
consider
by
this
searching in the
value.
index set, you know this is invalid or it's
Yeah.
originally zero.
The first two subsets, which are whatever the pixel index it contains, we say that it's not needed for us. And only the other gamma set which contains the data, they are considered the reliable ones.
Because that's the case, I mean, then you don't need to say that you set to 0.
Yeah, it's not set to 0.
Because it's the index of
Like we make three subsets. The first subset contains the impulsive noise one, the second subset contains the the incomplete observation we have is the PJK of omega, which contains contains the index set of those pixels which are reliable for us to complete the matrix completion problem. For the matrix completion, we use the minimization problem. That's the nuclear norm minimization problem. We do the nuclear minimization such that the Frobenius norm of the cube, the clean image which we are reconstructing now, and the P, that's the noisy part, is less than or equal to the size of the index multiplied with the estimate of the standard deviation of noise. That's the minimization problem which we do for the low rank matrix completion recovery. So, a paper like guaranteed by Faisal and Rick, they said that the nuclear minimization problem could guarantee the minimum rank solution. That's why they're using the nuclear norm minimization problem. And the matrix completion technique which this paper used is a fixed point iteration for solving the minimization. How they solve that technique is
What's a newcomer about?
nuclear norm.
Yeah.
Suppose we have a matrix X and we calculate the SVD of that matrix. Then so this sigma, it contains the singular values of all those things. So the sum of the singular values will be the nuclear norm of that matrix. So minimization.
The sum of those.
Yeah, sum of the singular values of the matrix.
Due to absolute value.
Oh, that's
Sigma.
I mean, do you take absolute values to the single value?
Yeah.
No, sir.
Just sum together?
Yeah, it says.
They are all positive numbers.
No, it doesn't necessarily.
Is that the absolute?
I need to double check.
Yeah, I remember it's the singular values are square root or square of the eigenvalues. So it should be all positive. So I don't remember, but I have some impression.
It's just the sum of the singular value.
Can you check SVD also? SVD.
like this. After we do the singular SVD, we get the eigenvalues and the eigenvectors. The singular value is the square root of the eigenvalue.
I mean, you
Singular
can
value.
make the single value positive or negative, but I'm just thinking like it doesn't matter. So I'm thinking if you don't take the square, it sounds complicated, but I guess it's like this. Because like the single value, you can make it positive or negative, depending on the basis you choose. Then you can force all the single value to be positive, then the Liu can learn just some of that, stuff like that. But I'm thinking like if you put a square there, it would be easier, but I don't know. Probably. So you have the Liu can learn in the previous page. Oh, I need the,
Okay,
the,
one
the,
second. Yes.
Why do you use here? Why do you use here?
Nuclear one is more efficient in recovering electron matrix. It's like printed paper. They put the algorithm.
Ah, that is so nice.
Can you explain by the use you can
Actually, no, but there's a paper by Faisal and Benjamin. They prove the procedure like saying nuclear norm is more efficient in recovering the low rank matrices.
So you want the matrix to be sparse in any case, right? So more like to be half linear independent. Then you expect at least if they are linear independent, for example, the rank is basically the size of the number of like non-zero single value. So intuitively, then instead of like forcing, like I have like so many number of like single value, I'll just like make the sum as small as possible.
Like if we reduce the nuclear norm, we are reducing the nuclear norm in the sense we are reducing the number of singular values.
Of course not exactly, but it's difficult to, so it's like compressed sensing, it's difficult to minimize the number of the non-zero value, right? But it's easier to minimize the sum of all the elements. So now I don't care about the number of non-zero singular value, I just want to minimize the total sum of singular values.
Is that mean the number of singular values will be equal to rank of the matrix?
No, no. Oh, okay. Number of single values, yes. Number of single values is just equal to the rank, right? Because like the transform you have is, what do they call it? I forgot. Because it's just a linear transform from that matrix and transform into your sigma, right? Then sigma obviously the rank is equal to the rank of the number of non-single values, so therefore the rank of x is just equal to the number of singular value. U and V are full rank, basically.
Now we have the missing elements in P, like which are the very limited values, and then we perform this matrix completion algorithm. So fixed point iteration algorithm is a popular algorithm in the matrix completion. They recovered it like first we consider a matrix Q which we need to recover, the clean image matrix, set all the whole of the matrix Q to 0. Then we perform iterations on that Q by reducing the putting its values until the time like we put a threshold E, which is the error tolerance in all of the matrix completion algorithm. We see that if the error tolerance is met up to 10 to the power of minus 5 or such value. So once the error between the Q is comes to 10 to the power of minus 5, or the number of iterations done will be 30, then the algorithm will terminate, and the final output Q which we get is the clean image. Here if we see the P is a term which is which contains both the noisy and the denoising, the PJK which we have, and the P omega which we see here is the one which has only those index elements which have the reliable elements, and all the other terms are considered to be 0. Yeah. And the QK is the one which we with the termination, with every iteration the matrix completion output would be in the QK. We calculate the next.
Where do we get sigma t there, down there? How do you find
Shrinkage operator. Yeah.
sigma t?
Sigma t. Here,
Sigma t.
this is a shrinkage operator d of x. So here, after calculating the r of k, we perform the shrinkage operator of that r of k.
Yes, but
So-
I'm saying like how do you do the shrinkage operator? Like how do you find sigma t there?
T is a already pre-assigned value. They consider a 3 threshold value which they consider.
Okay. So, but I lost it in this previous page. So I just
I'm explaining how the PJ from the minimum elements, how we recover the.
I mean sigma t is just a threshold. Like t is a threshold. You have a sigma the diagonal matrix. Then
It's
you
a
have like
diagonal
whenever it's
matrix.
smaller than that, you just dump the. I mean, whenever your single value is less than t, you just set it to 0.
No, T in the sense, what they say is during the nuclear norm minimization, for that purpose they consider the singular values to be of a threshold, like
Yes, yes.
0.2 here.
So how do we get sigma t from sigma?
How do we get sigma T from sigma?
Yeah.
Oh, now this is a sigma, right?
Sigma
The-
is, yes.
The whole matrix.
Yeah.
Now they put a threshold of, yeah, exactly what it is.
Yeah, that's what I said.
That's
okay.
what, sorry.
So the Q is still a 64 by M matrix, right?
64 by M matrix.
So you take mean of Q to get the final result. I mean,
Sorry.
Q is a 64 by M matrix. How can you get a 64 by 1 matrix to recover the pixel?
Oh, to recover the image?
Yeah, to
No.
recover.
First we calculate the Q64 by M1, and then from again, it has only the patches, right? From the patches we'll again synthesize the whole denoised image. This is not the complete denoised video. Now this Q64 by M, it has multiple patches. Again from that we will recover the video. The results of their algorithm is like this. They consider the video frame and then introduce some quantization noise, impulse noise and Gaussian noise, and then they reconstructed the video after the performances like this. It's the results of their algorithm.
When this paper? When is this paper published?
In CVP computer vision,
When was it?
2010.
one question. You reconstruct one picture with a sequence of the frames,
Yeah.
or
The
one
whole video.
whole video?
Whole video.
Who's the author again, Ima?
So,
Who's the group working on this?
it's from the Singapore University. National.
NUS?
No. Singapore.
Yeah, that's NUS. Right?
Oh yeah, NUS. Yeah.
Is there any comparison between this method and other?
Yeah. Then they compared this algorithm with the PCA method. The results are. I'll put those. Maybe I'll.
Another question. This is just for the video.
Yeah. Just for
Can I use for the single image?
Actually, I'm trying to implement that in single image. I'm not sure how much.
They find similar patches in the following frames. They can put into a matrix and try to complete that.
Yes.
If you do it in a single image, how do you find similar patches?
If I like right now what I'm doing is the database, it contains the faces of the similar images, right? Like many, so I'm trying to concatenate those into the patch matrix and then perform the matrix completion on it.
You have some data set, so
Yeah.
okay.
Data.
One question. In each frame, you consider fixed windows. For example, you have some overlap windows.
It's fixed windows.
And if we use the result, yeah, if just I mean that the iteration can use the iteration for the video, for the sequence of video. I mean that the result is better than this one. I mean that for example, we can use this one because you said that we just apply for all of the video.
Mm-hmm.
Can use this sequence, this video, and again apply this method on it.
Yeah.
And maybe the thing. Oh, they did check it out.
Actually, they will do the.
Yeah, I mean the iterations. We can use the iteration method for that, and maybe we can just.
Again, we need to do the whole procedure, like not leaving the adaptive medium for again the patch matching and then completion.
And what's the time for processing, for example, the sequence of video?
It's they considered a 30 frame video with a 354 by this pixel. They completed that in I'll check it.
Okay, thank you.
compare with the two techniques, two or three techniques, one is a VBM 3D technique. It's almost similar to the, but the VBM 3D technique, it doesn't have a pre-processing in its algorithm, like the adaptive median filtering pre-processing. So these people, they did the pre-processing and then checked for the results.
So how much performance gain they got in terms of dB or PSNR?
PS,
How do you get, oh, okay.
That's some table for the result.
it's 21.5 dB.
I mean, for which image and what noise?
For references.
First paper.
Computer vision. It's a language.
Oh yeah. The results. They use case feeding. It's case feeding.
Oh, is that the case?
Yeah, it's case feeding.
So here's